Okay, good morning, everyone. How did your homework go? Any questions from the homework? As usual, put them on chat and we go through them. Get going? Okay. 45 and 49, 55 and 61. Very good. Okay, so we start by order. So 45. And there are all bunch of limit problems. So we need to find the limit as x goes to infinity of ln 3x plus 5 over ln of 7x plus 3 plus 1. Okay, so we need to find the limit. So the first thing we do, always analyze. We do not jump to L'Hopital's rule without analyzing. We have to make sure we can apply it. It means we have to make sure we have 0 over 0 or infinity over infinity. All right, so let us study it. When x goes to infinity, when x becomes very large, let's look at the denominator first, because that's usually the problems here. When x goes to infinity, 7x plus 3 go to infinity. It becomes very large. So the input here becomes very large. Ln of something large is large. Slowly, not very large, but it's large. You're adding 1, so you're making it slightly larger. So this one actually goes to infinity. Now the numerator. So I have infinity here. Now I have to make sure I have infinity up here. When x goes to infinity, 3x plus 5 becomes very large. So the ln of something large go to infinity. So now this is type infinity over infinity. So I can use L'Hopital. So this is equal to L'Hopital's rule. It's the limit as x goes to infinity of the derivative of the numerator over the derivative of the denominator. Okay, so now it's just a matter of computing derivative. So this is equal to the limit as x goes to infinity of. Okay, so let us see. What's the derivative of ln of 3x plus 5? So that's the chain rule. Ln of something. So it's the derivative of the ln, which is 1 over 3x plus 5, times the derivative of the inside, which is 3. So that's the numerator. Now denominator. Again, plus 1, the 0 here. It's the derivative of the ln, which is 1 over 7x plus 3, times the derivative of the inside, which is 7. So I get that. Now I need to compute the limit. Now, usually we have always to be smart about things. So when I see something like a mess like this, I really won't keep it. I do some algebra to make it look nicer, because we know that we can simplify this algebraically. So before I even compute the limit, now I'm not doing limit. I'm just doing algebra, just to simplify it a tiny bit. So I will get the limit as x goes to infinity, and I use the property of fraction. So this will become 3 over 3x plus 5 times that over 7, which is the limit as x goes to infinity. I'm still doing algebra to simplify it a little bit, of 3 times 7x plus 3 over 7 times 3x plus 5. Now it looks actually much easier to deal with. It's not really as hard as before. And now I analyze this. When x goes to infinity, again, what happened? The numerator goes to infinity, but it's an easy numerator now. And the denominator goes to infinity. So this is type infinity over infinity. So you can use L'Hopital's rule again here in this simple problem. And then you get the limit of the derivative of the numerator over the derivative of the denominator. Now, what's the derivative here? 3 is a constant. We don't have to worry about it. Derivative of 7x plus 3. So it's going to give me 3 times 7 over 3 times 7, which is equal to 1. Okay? Make sense? Right, so usually, I mean, we use L'Hopital's rule. The only remark I have to tell you is that you have to be careful. Sometimes if you can simplify your expression, simplify it. Otherwise, if I had used L'Hopital's rule here, which I could have done it, because when x goes to infinity, this will go to 0 and this will go to 0. I will have 0 over 0. But if I use it here, the derivative becomes messy. And actually, I think we will go into a vicious circle. So by simplifying it a tiny bit, actually, I made my problem way easier. So this is something you have to be careful with as you're doing the problems. Okay, now let's look at 49. See what this is about. Already, so 49, it's the limit as x become close to 2 of the following: x squared minus 4x plus 4 over sine squared, but remember sine squared is nothing more than sine x to the power 2. Very good. Now let us analyze this. First, the numerator, denominator, because this is, if the denominator doesn't go to 0, probably less likely, or doesn't go to infinity, means I really don't have issues. So I start with here. When x become close to 2, the denominator become close to what? You guys tell me. The denominator. Go ahead. The denominator become close to what?
0.
0, because? You're right, because?
Because sine of 2 pi is 0.
Right. When x become close to 0, 2, look at the inside. Pi x become close to 2 pi. Okay, that's how we do it. So the sine square of it, the whole thing, sine of 2 pi is equal to 0, become close to 0. Now the numerator. So now I know I have an issue here. The numerator, when x become close to 2, this become close to 4. 4 minus 8 minus 4 plus 4, this is going to become close also to 0. So definitely problematic. Definitely problematic. All right, so L'Hopital's to the rescue. This is equal to, by L'Hopital's, it is the limit of the derivative of the numerator over the derivative of the denominator. But now the denominator involves sine square. So I will immediately rewrite it as sine pi x to the power 2, because I need to differentiate this expression. Now, so this is equal to, now I am differentiating. Numerator is 2x minus 4. There is nothing hard about it. Denominator. So that's the sine of something squared. That's the chain rule. So I need the chain rule. So it's going to be the derivative. The derivative of the outside, which is the outside now is u squared. It's 2 times sine pi x times the derivative of the inside. So the derivative of the inside, the derivative of sine of pi x, it's derivative of the outside, which is cosine pi x, times the derivative of the inside, which is pi. Okay, so I get that. I think there isn't much in terms of simplification here. There's nothing I can simplify. So I just go ahead and find the limit. What happens when x goes to 2 now? When x goes to 2, I will have Okay, I seem to have a mess again. I'll have 2 pi in here, so that goes to 0. And cosine 2 pi, that goes to 1, but anyway, this will go to 0. Numerator, go to 0. All right, again, type 0 over 0. We know what to do. L'Hopital's rules again. So, and this time it's going to be resolved. Okay. The derivatives, L'Hopital's rule again. Derivative of the numerator, derivative of 2x minus 4, it's 2. So definitely it's being resolved. Denominator, okay, here I have a product of 2 functions. So, and 2 pi is a constant. I don't have to worry about that. Now I have a product. I have to use the product rule. The derivative of sine, which is cosine pi x, times pi cosine pi x, product, plus. So from here to here, product rule. Plus sine pi x times the derivative of cosine, it's minus sine pi x times pi. Okay, so derivative of sine is cosine pi x times the derivative of the inside times the cosine plus sine, derivative of cosine minus sine pi x times pi. And now let us see what this is going to be. The numerator is safe. We know it's safe. It's 2. The denominator, when x becomes close to 2, this expression becomes close to what? You guys tell me. When x becomes close to 2, analyze it. Tell me this becomes close to what? I'm listening. I need a sip of water.
Pi.
Because. You're right, because.
Cosine of 2 pi is 1. Cosine of 2 pi is 1, so 1 times 1 is pi, I guess, yeah.
Very good, absolutely pi. Because if I put 2 for x here, cosine 2 pi 1, cosine. Now, what about this expression? When x becomes close to 2, I'll have sine 2 pi, that's a 0. I don't have to go any further. That's a 0. So finally, the limit is going to be 2 over 2 pi times pi, pi squared, 1 over pi squared. Okay? All right, let's look at the last two, and hopefully this is the it's 55 and 61. Okay. Any questions? Okay, so let's look at 55. And it is the following. It is the limit as x become close to 0 of cosecant 6x times the sine of 7x. Okay. So what's the limit of that as x goes to 0? Okay, again, we're gonna analyze this thing. What do you want me to do? What do you guys want me to do? Any input, any ideas? Make a denominator. Very good. Change cosecant. You know, cosecant. Okay, what can you change cosecant? Because the cosecant is it's a mess to deal with. So change cosecant. So what's cosecant? Cosecant is 1 over sine. Okay, so it looks like kind of a messy, but cosecant is 1 over sine. So now if I change it, this will become what? I now change it. I replaced it by what it means. So this is 1 over the sine of 6x times the sine of 7x, which is basically just before, we're not computing limits. So from here to here, I'm still basically algebra. From here to here, algebra. I'm not really doing anything. So that's the limit of sine of 7x over the sine of 6x. So now I am in a very easy territory. It's not really hard anymore because basically I did the substitution. Cosecant, I just substitute by 1/6x. And now that's very simple. When x goes to 0, this will go to 0, and this will go to 0. So type 0/0. I can use, now I'm using L'Hopital's rule. Now I'm using it. I wasn't before. So that's the limit of derivative of sine 7x is the cosine 7x times the derivative of the inside cosine 6x times the derivative of the inside. Now as x goes to 0, there's 7x goes to 0. Cosine of something close to 0 is 1. This is 1, and I end up with 7/6. Okay, so the problem looked kind of messy at the beginning, but actually it was not that bad. Very good. So my last problem, hopefully with that, and this is 61. All right, so before I touch 61, I need to talk about one more type of indeterminate form. There are a lot, but I will cover, the one I will cover are 0/0, infinity/infinity, 0 times infinity, and this new one called infinity minus infinity. So before I do 61, I introduce this indeterminate form. So indeterminate form of type infinity minus infinity. So what do I mean of type infinity minus infinity? Means the following. So suppose I have two functions, and when x become close to a, f of x goes to plus infinity. And g is another function. This is equal to infinity. Then the limit as x become close to a of f of x minus g of x. So now as x goes to infinity, as x goes to a, f goes to plus infinity, g goes to minus infinity, to plus infinity. So this will become, is called indeterminate of type infinity minus infinity. Okay, so every time I introduced an indeterminate form, I try to explain to you why it is indeterminate, why large minus large is actually could be anything. Why? I mean, students tell me, okay, infinity minus infinity is 0. And this is wrong because infinity is not a number. Infinity reflects an idea that something is growing a lot. And this is not a number. So it's not 0. 0 is not in the picture. It's something that become large minus something become large. Why it is indeterminate? Let me see. I want to ask you to give me the following. Give me an example. I want you to do that. Of a function f of x, a function g of x. Okay. Such that the limit as x goes to infinity of f equal plus infinity, you guys have to give me those. The limit as x goes to infinity of g of x equal infinity. But the limit of f minus g, I'll take in, I want this limit. Let us say I want it to be large. Why not? Give me an example. And then I'm going to change the scenario. Because I have to convince you why large minus large is not really. Infinity minus infinity is not infinity. It's not 0. It could be anything. That's why the word indeterminate coming from. Okay, who can give me an example?
We can make one e to the x.
We can make one e to the x. I like that. Make the other one what? I want g. And I want to go to infinity.
X cubed, maybe?
What?
X cubed?
X cubed. Okay. So now what happened here? Which one goes to infinity way, way, way faster, based on what we did yesterday? E to the x or x cubed? Back to you.
E to the x.
Way
E
faster.
to the X.
E to the x, way, way faster. Remember the table we did yesterday? Remember, because this is, I really want it to be really, really clear. If I take e to the x and x to the power 3, let me take x to be 10. What e to the x? Watch carefully. I want you to fully interact with that idea. E to the x, it means e to the, sorry, not, so e to the x, e to the power 10 is 22,026. X cubed is 10. Okay, it's 10,000, it's 1,000. And this is already 22,000. If I take the difference, 22,000 minus 1,000, this is really going to be very basic, it's going to be large. Watch if I take even x larger. I'm going to take x to be 20. So this is going to give me 8. However, e to the 20, look how large it is. Okay, 1, 2. It's 485,165,000. Sorry, it's 485,165,195. Look how big is e to the 20. Look how big is 20 to the power 3. So when I start taking only x to be 20, the difference is going to be really, really, really large because this is taking over. And if I take even larger x, you can imagine what's really going on. So here, when I'm going to take the limit of ex minus x cubed, is going to be very large. Okay. Now, I want to switch the scenario, and then we're going to work out problem. I want you to give me that. I want f of x. I want g of x. Okay. And I want infinity because it's easier. F of x goes to infinity. I want g to go to infinity. And I want the limit. Let me pick a number. Okay, I want the limit, even though it's large minus large, I want the limit to be, I don't know, 1. So that's the idea of infinity minus infinity indeterminate. I can have any scenario possible. Okay, a little bit tricky, but when you guys see the answer, you will realize, oh, I should have thought about it. Every one of you, f(x) can be, so I see something. Okay, actually another one. Zach, you gave me a nice example for the first problem. Yeah, very good. Okay, now I have one answer, and it's a nice answer because it shows you how simple it could be. So she gave me x squared plus 1, which is definitely go to infinity, and she just gave me x squared, which is goes to infinity. And now when I'm going to take the difference, I'm going to have the limit of x squared plus 1 minus x squared. Both goes to infinity. But the answer is what? Because they go to infinity almost very similarly. Okay, so that's where the word indeterminate coming from. So we got infinity. Actually, I would like also to write Zach gave me the following. 5x here, that's another example, and 2x here. That's another nice example because both goes to infinity. And when I take the difference, I get 5x minus 2x, which is 3x, which is definitely go to infinity. Another very nice example. So large minus large could be anything. So the question is how to handle those kind of limit. Of course, L'Hopital's rule doesn't apply because it doesn't have the right type. Usually, we manipulate algebraically. So most of the time, we kind of find a common denominator so we can turn the problem into a problem where I can use L'Hopital's rule. So a lot of time, not most of the time, a lot of time, if there is a possibility of finding a common denominator between f and g, we do that so we can use L'Hopital's rule. So it's algebraic. So to solve those algebraic manipulation so that we can get rid of infinity minus infinity. Okay, with this in mind, I will look at your last question, which is 61, I guess. Yeah. So now I look at 61. Okay. Number 61. So here I have the following. The limit as x become close to 0 from the positive of cotangent x minus 1 over x. Okay, so let us analyze. Now, when I see cotangent, what do you think the first thing I will do? To understand cotangent, you know, we understand sine and cosine better. We all know that. So cotangent is the cosine over the sine. Okay, so rewrite exactly because it's easy. So I'm going to rewrite it and then analyze it because it's easy for me to analyze. So it's cosine x over minus 1 over x. Okay, now analysis. When x become close to 0 from the positive, positive is going to play a role. And you will tell me why positive is going to play a role. What happened to cosine over sine? All right, so let us see this one. Sine x is, okay, that's x. That's the sine. Okay, so that's the sine. So when x become close to 0 from the positive, that's how my x become. The sine x take small value, but positively small. So this is small, if you want. So it goes to 0, parenthesis, but positive. Positive. The cosine, when x become close to 0, the cosine become close to 1. So now the whole thing is 1 over something small, positively small. The whole thing will become close to plus infinity. Okay? Now what about 1 over x? This become close to what? When x become close to 0 from the positive. Quick, quick.
0 approaching.
Not indefined, not indefined. Why not indefined? Who can answer the question? Crucial.
Because it's close to 0, not 0.
Exactly. X is never 0. X is never 0. X is close to 0. Crucial. The limit does not take x 0 into consideration. When I'm computing the limit, I never put 0. I put something close to 0. Be very careful with this idea of a limit. It's very subtle. X is never 0. X takes value closer and closer to 0. So x goes to 0 from the positive. What's in my mind is 0.01, 0.001, 0.000001. I never say x equal to 0. Very important. Otherwise, everything is undefined. Now, when x becomes close to 0 from the positive, this becoming small and positive, that's plus infinity. If they hadn't told me x goes to, if instead of 0 plus, they put 0, I have a problem. Because if they put 0, 1 over x, the limit doesn't exist. Because when x goes to 0, 1 over x, the limit doesn't exist. Because from the positive, it's plus infinity. From the negative, it's negative infinity. It does not exist. So I really need this to make sure I'm going to plus infinity. So infinity minus infinity, absolutely indeterminate. So how are we going to do it? As I said a minute ago, a lot of times, let me write now this one simply. I'm not changing. I'm just going to rewrite it. So now after I analyzed it, so now I have cosine x over sine minus 1 over x. So one of the trick we use is find a common denominator. Okay, because hopefully I can use L'Hopital's after that. So now, so this is equal to common denominator. Common denominator. I will have the limit. So that's one of the trick we use for infinity minus infinity, if possible. Okay, common denominator is going to be x times sine x. That's the common denominator. So this has to be multiplied by x. And this has to be multiplied by the sine. Okay, and now we analyze again. When x becomes close to 0 from the positive, this is definitely a 0. X become close to 0 times cosine something that's close to 0 is 1. So that's a 0 minus sine that also goes to 0. Now I have type 0 over 0. L'Hopital's rule is in order. So that's how we manipulate so we can use it. So this is equal to now L'Hopital's rule. It's the limit of. Very good. Derivative
I have a
of
question.
what?
So when it comes to infinity minus infinity, so we just have to rewrite it if we get something like that?
Yes, and find a common denominator.
Okay.
But this is not always the rule. I mean, this is, and this, when infinity minus infinity, I don't have very specific rule. I have guidelines, and there's a difference between guidelines and rules. Okay?
Okay.
So one of the guidelines, if possible, is try to write it and find a common denominator. And that's a guideline. Sometimes they don't work. So we have to be creative about it. But that's one of the tricks we use. Okay? So now derivative. Okay. Derivative of the denominator. That's actually the numerator. Why not? This is a product. I have to use the product rule here. So I will have derivative of x is 1. I will have cosine x plus x. Derivative of cosine is minus sine. Minus the derivative of sine is cosine. Denominator. Product rule. Derivative of x is 1. It's sine plus x times cosine. Okay, now, of course, we're smart, and I immediately see plus cosine minus cosine. So just algebra now, because when we can simplify something, we do it. When we can simplify, we do. So I will have minus x sine x, because those could be simplified, over sine x plus cosine x. And that's give me what? When x goes to 0. Oh, I see L'Hopital's again. This become close to 0, and this become close to 0. And this goes to 0. So type 0 over 0, and L'Hopital's rule in order. I hope that's the last time. Equal. All right, again. Product rule. We have minus sine x plus x cosine x over derivative of sine, cosine. Good. Plus. Again, product rule. Cosine x plus x times the derivative of cosine is minus sine. Are we out of the loop yet? Okay, let's see. When x goes to 0, so I have cosine plus cosine, that's 2 cosine. So that's I have 1 here, and this goes to 0. So I'm definitely out of the loop because I have 2 plus 0 in the denominator. I seem to be safe. My numerator, this goes to 0, this goes to 0. But I don't have any issue anymore because my denominator is 2, 0 over 2, which is 0. Okay. Any other questions? Right. So I'm gonna give you one little one because I wanna make sure we know how those functions comes up a lot. Question number one, this is simple, not hard, but I wanna make sure. What's the limit of e to the minus x as x goes to infinity? Before I move on. All of you.
Zero.
Important limit, 0, because absolutely correct, because
It's big 1 over e to the x, which
exactly.
becomes
Exactly. E to the minus x, e to the minus x is 1 over e to the x. Now, when x goes to infinity, e to the x goes to infinity. 1 over that equal to 0. So it's a limit that comes up a lot. I definitely want to make sure all of you can do it. Let us say I have that. Again, I give you all 2 minutes to figure out the limit. There's another limit that comes up a lot. Analyze it. Analyze it. Tell me what to do. Anyone? Any idea?
I got 0.
You got
I
0
think I'm
because,
I don't
as
think
usual,
I'm
you have to
right, but
justify. What?
so I just rewrote e to the negative x as 1 over ex, and then I made the fraction into x over ex.
Okay, good.
Substituted.
Very good, very good, very good, very good. I will rewrite it. Okay, rewrite, exactly. But before I rewrite, each one of you is correct. What you guys are telling me and writing is correct. But if I analyze it as a limit, which type limit is that? Before we rewrite it, what type limit this is? When x goes to infinity, this one goes to where? To infinity, right? E minus x goes to 0. So that's really type 0 times infinity, which we know is indeterminate. So rewriting it was absolutely the correct way to do it. Okay, so that's going to be the limit x times 1 over ex. But of course, we're not going to keep it like that. That's x over ex. Use L'Hopital's rule, and you end up with honest to goodness 0. Okay. So those limits are important because e minus x, ex, those are functions that comes up a lot with us. All right, so these are the type. There are other indeterminate form, but these are the type that comes up a lot, the most. So infinity over infinity, 0 over 0, 0 times infinity, and infinity minus infinity. Those are the type. There are others. I will just not cover them this semester. Part 2. So now we're going to start moving. Basically, at this stage, we are done with what we call the differentiation. It means we are done with the idea kind of derivative. In a sense, we've learned, given a function, we've learned totally how to find the derivative. We interpret the derivative geometrically as the slope of the tangent line. And the meaning of it is how fast things change. So if my function represented the position function, it means you have an object which is moving. And basically, I know the distance the object traveled all the time. The derivative gives me how fast the object is moving, how fast the distance changes in question. And then we learned what does the derivative tells me about the function, in the sense that if the derivative is positive, function increasing, derivative is negative, function decreasing. And we learned what the second derivative tells me about the function. The second derivative measures concavity. So this is basically the main ideas, at least for this course, about the differentiation. Now we're going to start moving backward. And this is going to start the basically calculus 2, but now we're going to start building blocks for calculus 2. So we're going to start moving backward now. It means we're going to start with the derivative, and you're going to start going backward and starting to look for the function whose derivative is what we know. And this process is going to be called anti-differentiation. So section 4.9, that definitely we're going to start today. Section 4.9, anti-derivative. Anti-derivative. Okay, so the idea is that we have a function f, I'm going to call it big F. What we've learned so far is differentiation. We start with a function, we found its derivative. Okay, that's what we learned. Now we're going to start moving backward. It means I know the derivative. I will give you the derivative. And the question is how to find the function. So I'm going to give you f prime. And the question is, what is f? The process of moving backward is called anti-differentiation. Anti-differentiation. Okay, so that's what we're going to do starting today. And calculus 2 will actually, basically, part of it, not all of it, will work with this process. All right, so today we're going to, so first, what's the word antiderivative? The definition. Suppose I have a function f, little f, okay? The function f, whose derivative is little f, is called the antiderivative. So definition, we say that, and for some reason every book uses this notation, big F. We say that f is an antiderivative of little f if the derivative of f is equal to little f. So we say that capital F is an antiderivative of little f if when we differentiate f, we get f. So that's the definition of antiderivative. So let us a little bit practice this definition before we move on. All right, so for example, take a new place. Suppose I give you the example 1. Okay. Suppose I tell you, let f of x equal a simple one, f of x equal to x. Find an antiderivative of f. So find antiderivative. So f of x equal to x. I want you to find antiderivative. What does it mean? It means I want you to find a function. When you differentiate it, you get x. So x is here. X is the derivative. Now I want you to go back. What is the function? When you find this derivative, so from here to here is derivative, from here to here is antiderivative. So now I know the derivative. I know I need the function back. All right, so we're gonna guess, and then we learn the rule. We're gonna guess first. So what is the function? When I find its derivative, we get x. So we have really to think about how does the derivative work. So let's see how the derivative work. The derivative work like this. If I have x to the n, what the derivative do is actually take a power away. That's what the derivative do. Now we're intuitively we're going backward. So what is the function when I find its derivative? I'm going to get x. So what this should be? What should be my starting point? Which is a good candidate. And keep this in mind. The derivative takes away a power. X squared is a good candidate. Okay, that's a good candidate. So let us work with x squared. All right, so we're just working now. I don't have answer. So if I take x squared and I find its derivative, I get 2x. So x squared is not bad, but it's not good also, because what I want is x. If I take x squared, I'm getting 2x. So how can I manipulate the whole thing to get x? Okay, I'm not giving you answers yet. Now we're still thinking. Okay, the idea is that, okay, if I have 2x here, you know, this 2 is bothering me. So why don't I basically, to compensate for this 2, why don't I take the half of x squared? Basically to compensate for this 2, the half of it. Okay, let's see what's the half of it is. It's a half, the derivative of that's a constant, times the derivative of x squared to x. This will give me x. So x squared is a good candidate because the derivative takes away 1 from the power. So to get x is the first thing, a good candidate is to start with x squared. But we run into the problem that the derivative of x squared is 2x. So the idea is that how to compensate for this, that, you know, why don't I take half of x squared? And that's the half and the 2 will simplify, and I get x. So my good candidate has to be here, 1/2 x squared. So let's write this down. Let's rewrite this down. So now what's the answer is, after we analyze it, so what's the correct answer? So antiderivative of f of x equal x. Okay, so if f of x equal x, then the antiderivative is a half x squared. It's a half x squared. And this is because when I take the derivative of half x squared, I get x. Okay, very good. Now, here's the question. Who can give me another one? Who can give me another one? Who can think of another one?
Would it be 1/4x to the power of 4?
Nope. By no stretch of the imagination. Why? Why? If I take what you gave me and I differentiate it, so I will take everything you guys gave me. Okay, I will write your answer on another sheet of paper. So you gave me that, right? Right? If I find the derivative of this, what do I get? 1/4 is a constant. The derivative of x4 is 4x cubed. I get x cubed, and I want x. Okay, so doesn't work. we can think of another function that when I find its derivative, I also get x.
Can it be like a simple function? Because what about like 3x?
Anything, anything. And
What about like
okay?
3x or something?
No, what's the derivative of 3x?
X or
What's
oh no,
the-
3. Oh no.
What?
We could do 1/2 of x squared plus 5.
We can do 1/2 x squared plus 5. Does it make sense? Does this make sense? What's the derivative of 1/2 x squared plus 5? Derivative of 1/2 x squared is x plus 0, because that's a constant. That's equal to x. Okay? So there are a lot of antiderivative. Now the picture is a little bit clear. I can take plus 5. I can take plus what here? So is 5 the only number you can think of? Can I think of another number? What about if I take plus 10? Will this work?
Yeah.
Yeah. And geometrically, why, we have a lot of them. So f of x 1/2 x squared, f of x 1/2 x squared plus 5, as you realize, this is nothing more than the shift. So graphically, what's really going on before we start, going rules and stuff, graphically, what's going on? You guys gave me one function, whose derivative is x. So let me draw it here. This is 1/2 x squared. Okay, this is 1/2 x squared. Okay, and what's the property of this function? If I take any point, this function, the slope, any point, the slope here is equal to x. So if I take x equal 2, I know that the derivative here, which means the slope of this tangent line, is going to be f prime at 2, which is 2. If I take 3, the slope is going to be 3. Now, if I take this function and I just shift it up, I don't do anything with it. I shift it. So the same function, but being shifted up. Okay, so this is the one you guys gave me. 1/2 x squared plus 5. Now the question is, will the derivative of this new function will be the same as the derivative at the old function? Will those two, so at every point, so at the point 2, let me take this point 2, will both functions have the same derivative? So I fix a point 2 on the graph of 1/2 x squared and on the graph of 1/2 x squared plus 1. Will the derivative, geometrically I'm thinking, will those two derivatives be equal? What do you think? Remember, this is a shift. Means I'm taking this one, I'm just shifting it up. I'm not really stretching. I am not doing anything. I'm just taking it and shift it. So because I'm shifting it only, the slope here have to be exactly the same because I'm just shifting. Means the derivative, slope of the tangent here, the slope of the tangent here are the same. Means the derivative are actually the same. So if I take this function f and regardless, and I shift it up or down, shift it, it means I'm just making it and bringing it down. I bring it down, shift it. So I'm not changing the curvature. I keep the derivative the same because the slope are the same. So what I mean that, the idea is that if you have one antiderivative, if you have one function whose derivative is x, taking this function and shifting it up and down will not change the derivative, because it will not change the tangent line. And that's exactly what's happening here. That's really what's going on here. You gave me one function whose derivative is x, but then shifting this function up and down will not change the derivative because the slope is not really changing. So for that we say, and then I stop. For that we say that the most general antiderivative of f of x equal x, so we talk about the most general one, is going to be half x squared is the basic one. That's really what the one that matters, plus c, where c is any constant, is a constant. So this reflects the idea that I have a lot of antiderivative, but all of them have a very specific format. All of them has half x squared. That's the basic piece because the derivative of that is x plus a constant. So half x squared plus 5 plus 10 plus 15. So we have a lot of them, but all of them have this shape. The basic one plus a constant. Okay. All right, I take you from there tomorrow. And please, so you will not have homework. The only homework you have for tomorrow is the one I've assigned for today. So you guys finish it. And this will give you the chance to work on your review for your exam. Please do the review for the exam and ask me questions. Okay. All right. Bye-bye and see you tomorrow.